now until the beginning of July, and the first yeah. So now the chair today is Meng Chen from Shanghai. So I'll pass to over him.
Okay, shall we start?
Yeah.
Yes, please.
Okay, so I feel happy to introduce two talks from China mainland today. So the first speaker, Dr. Zhou from the Shanghai Center for Mathematical Science. He will talk about word crossing for K-theoretical quasi-map invariance. So now, so Zhou Yang, please.
Zhou Yang, can you turn on your microphone? We cannot hear you.
Sorry. Can you hear me now?
Yes.
Yeah, okay, thanks for the invitation. And I'm very glad to talk about a joint work of Ming Zhang and myself on K-theoretic quasi-map word crossing. So to fix notation, let me first say a few words about K-theory as a intersection theory. In this talk, say M is a space. So here space is most of the time it's a dilemma stack, and sometimes it's an Artin stack, but of a very simple type, Y modulo C star, this quotient stack, where Y is again a DM stack. So given such a space, we can define several groups. So this is a Grothendieck group of coherent sheaves on M. And this is a Grothendieck group of vector bundles on M. And we know that, so this is a ring. And K lower zero naught is a module. Over K up to 0. And when it's a quotient stack, then this is identified with the equivalent K theory of the thing upstairs. I forgot to say, this is everything is over C in this talk. And we want to consider very singular spaces. So we do make a distinction between these two groups. And we view this as a homology and view this as an analog of the cohomology. And we have natural functors. So this one has a proper push forward. And so this one has pullbacks because you can always pull back vector bundles and preserving exactness. So if in particular, M itself is proper over C, then we can take the push forward of a K-theory class where P is a scaffold map to a point. This one is identified with the Euler characteristic of a sheaf F. It also makes sense for a K class. This is in K0 of a point, which is canonically identified with the ring of integers. where F is just any K class on M. So this is a holomorphic Euler characteristic, and this is an analog of taking the degree of a cycle or taking the integration of differential form. And so this is an intersection theory we want to use to count curves to define counting invariants. So what are the invariants we want to count? They're called K-theoretic Gromov-Fitting invariants. It's an analog of Gromov-Fitting invariants with the intersection theory, the K theory, and it does have some interesting properties. So first, let this be the moduli of stable maps to X, where X in this part is a smooth projective orbifold. Projective just means the coarse moduli is a projective variety. So this one is the moduli itself is a proper DM stack with so-called virtual perfect option theory. So itself, it could be very singular, but the deformation theory looks like this is embedded into some smooth thing and defined by the zero section of by section of a vector bundle. So it looks like that, although only on the level of obstruction theory. But that's enough to define the so-called virtual phenomenal class. So it's just a class in the Euro-Chow group. And the so-called virtual structure sheaf. It's not a sheaf, it's a class in K lower 0 of the moduli space. So if it happened that the moduli space itself is smooth of the expected dimension, then this virtual phenomenal class is just equal to the Euro phenomenal class. And this virtual structure sheaf is just equal to the usual structure sheaf. But that almost never happens, especially in higher genus. Nevertheless, we have this virtual structure sheaf and virtual phenomenal class that play the role of the Euro ones. So we have the evaluation maps. So if X is orbifold, then this takes value in the so-called rigidified inertia stack. But you can ignore that if you don't want to worry about orbifolds. And for any given classes, in the upper K0, this should be thought of as imposing incidence relations of the curve we want to count. Then we can define the K-theoretic correlators. This is defined to be just replace the integration by Euler characteristic and the virtual structure sheaf times you impose incidence relations by capping with the pullback of those classes by the evaluation map. The evaluation map just takes the value is just the map evaluated at the marking, the ith marking point. So this is a Euler class, virtual holomorphic Euler class. This is a integer. So this is unlike the Euro Gromov-Fitting invariants. When the Euro Gromov-Fitting invariants are usually rational numbers because the modular space is an orbifold. But in this case, we are just computing the alternating sum of dimensions of cohomology groups. So it's automatically integer. So given a target manifold X, and given some classes and some discrete data, we can produce canonically some integers. So these integers are these are invariants of the target manifold. And these integers are usually very difficult to compute. And their generation functions, just like Gromov-Thelian invariants, have very nice properties. So for K-theory, it actually has more structure that doesn't appear in the Euro cohomology theory. So it's called SN equivariant structure. So this modular space, I'll just denote by M for short. So this one has a natural SN action, where SN is just a symmetric group. So it commutes the unmarked points. And the quotient, the geometric meaning is that it parameterizes just maps with unordered markings. So first of all, this natural appears even if you start with the ordered markings, because if you look at the boundary of the moduli might be a stable map from curves like this. If you want to split off the components, then this becomes markings, and these markings are naturally unordered. So it naturally appears when you want to study the structure of those invariants. And it's interesting because, for the virtual fundamental class, we know that so if you push forward things from upstairs to downstairs, you just get a factor n factorial, because this is a SN torsa, and the pull back and push forward just multiplies by n factorial. But for the virtual structure sheaf, we only know that the pullback are related by this, but we almost never have this one. Because just in nice case, this is a Euro structure sheaf, then the pullback should be a vector bundle of rank n. The right-hand side is just a line bundle, right? So recall that in defining the invariants, we're always pushing forward, right? Pushing forward to a point. So it does have a, so looking at the SN equivariant structure does give us more information. So this motivates the following definition. So given alpha in K cross on the target, then we can make it SN equivariant by taking the box product. Then we can consider the product of all these evaluation maps. And this map is also naturally SN equivariant. So we can define the invariance as this. So all this invariant equivariant K classes descends to the quotient by SN. Also, the evaluation map also descends to there. So we can do everything just SN equivariantly, where P is a map. to not to point, but to point modulo Sn. So what is this? This is a virtual. This is a in K-theory class of that, of the classifying space. This is just a ring of virtual representations of Sn. So we get not only integers, but virtual representations of Sn. Okay. And the previously defined Euro invariance is related by this enhanced invariance by just, this has a natural from virtual representation, there's a rank function to Z, just taking the rank of the virtual representation is well defined. It's just a rank of this as an equivariant invariant. And more interestingly, we can define this Sn invariant. This is Sn equivariant. This is Sn equivariant. This is Sn invariant. So it's defined to be the rank, just the Sn invariant part of this virtual Sn module. This is again in K-theory of a point, which is an integer. Okay. So yeah. So the advantage, the one disadvantage of this equivariant theory is that, so if you vary n, you want to write down a generating function. You want to generating function for the invariants, but you can't sum them up because they are representations of Sn for different n. But this one, they are just integers, you can sum them up. So one solution is that just generalize the definition. Just take alpha to be in some so-called lambda ring. You can think of this as a representations ring of GLN, but you take the limit as n go to infinity. So you take the alpha to be in some sufficient and generic lambda ring. So for example, if you take it to be a representation of GLN, it means that you tensor. So this is a virtual Sn module. You tensor with the representation of GLN for some V, where V is a representation of GLN. You take the invariant part, you get a representation, virtual representation of the same GLN. And by the sure while duality, that gives you enough information to recover this Sn module. So the upshot is that if we generalize the definition a little bit, then this invariant, Sn invariance, it's a little bit awkward to say that. So this Sn invariance already contains enough information. Okay, and similarly, you can generalize this definition a little bit by considering first a bunch of Euro insertions and then a bunch of equivariant insertions. You take the invariant part, where you have n plus k markings, etc. Generalization 1 and generalization 2, okay, etc. Okay, you can let some of the markings to be ordered and the rest to be unordered. Okay, so that's a quick review of Poisson map of K-theoretical fitting invariance. Okay, I forgot to say, so this was first defined by YPD, and then the equivariant structure, because K-theory was first considered, as far as I know, by Giventhal. And it was shown by Giventhal Tomita that this K-theory invariance is equivalent to the Euro competing invariance, but in the sense that if we know everything about the moduli of curves, so including all this curve, the loci of the curve with non-trivial automorphisms, etc. But that's practically impossible to work out. So, the equivalent should be some very sophisticated relation. Okay. Now let's move on to quasi-map invariance. So quasi-map invariance is also analogous to the Wong-Quinn invariance defined by stable maps. So to motivate, let's look at a special case. So maybe the most famous one, my favorite one, is the quintic Calabi-Yau threefold. Let me just use this equation just to be concrete. Then, so given this target manifold, then a map from a curve to X is equivalent to, it's very elementary that it's equivalent to a line bundle over C plus 5 sections such that, so first it had to satisfy this quintic equation. And then this base locus has to be empty, is equal to empty. Okay. 5 non-vanishing sections of a line bundle give a map to T4 and satisfy the quintic equation. Okay, so for the quasi-map is just a very simple modification of this definition. The left-hand side, let me write just quasi-map. And this becomes a definition. And the right-hand side is just the same data, but the requirement is a little bit different. Requirement that, so this thing is no longer empty, but it's required to be finite and disjoint from special points. So special points are defined to be the nodes, the curve, the nodal curve, and the markings. So this is just a quasi-map. Well, you may say, well, what's the difference from a rational map? The difference is that here we don't, we not only remember the map that's generically defined on C to X, but we also remember this line bundle. And that makes a big difference when you form moduli space, when you form families. And also the differences, even if you look at the one single map, it makes a difference if you consider non-abelian groups, which I'm gonna introduce. Okay, so this can be generalized by noticing that X is actually equal to this affine cone modulo C star. You take the GIT quotient, the standard character. And here is just the unstable locus where all the 5 coordinates are 0. You can see that this unstable point corresponds to this one. And so this gives us a generalization to X is equal to W modulo G, where W is a affine with mild singularity, and G is a reductive group. There's a crucial condition that the semi-stable locus is equal to the stable locus. So there are much more examples, interesting examples, and but for the purpose of this talk, because the wall crossing is actually quite universal. It doesn't really depend on the target. It's a uniform phenomenon. So we can just keep in mind this special example. Okay, so let me introduce more terminology before moving on. So in this example, so recall that the coordinate map is just C, L, and phi 5. So this phi equals 0 is called base locus. And the degree always refers to the degree of the line bundle. If I see the degree of one irreducible component, it means the degree of the line bundle restricted to that irreducible component. And you have if you have a x inside this base locus, a base point, then the length at x, length of the base locus at x is defined to be the minimum of the vanishing orders at x. So it's just the length of this subscheme at x. Okay, so recall that in a stable map classification, so when these 5 fields want to develop a common 0, then we usually bubble out a Riemann sphere to prevent that to happen, to just separate all the zeros of these 5 fields. Physicists always call these fields. But in quasi map, we allow the zeros of these 5 sections to collide as long as they remain finite and disjoint from special points. So it means that there are different, more limits added to this one parameter family. So in order to get a proper dilemma stack, we need to add some stability conditions. Okay, so the most general one was defined by Kyokan, Clantin, Molik, Kamen, Molik. So let's say the domain curve is like this. Then we call this P1, smooth P1s with one special point. We call them rational tails. And the smooth P1 with 2 special points. We call them rational bridges. A marking is also a special point, so this is also a rational bridge. So the stability condition is just controls when you keep the base points and when you shoot out a rational tail. So given a rational number, positive rational number, a quasi map is called epsilon stable if every rational bridge has degree positive and every rational tail has degree no less greater than 1 over epsilon, and every base point has the length not too big. Plus requirement on 2 special cases. If you have a smooth elliptic curve, smooth curve with just 1 curve, no marking, then degree is positive. P1 with no marking, then degree is at least 2 over epsilon. Okay, so let's forget about these 2 special cases, not quite relevant. Okay, so having this stability condition, then they show that if we denote this by this, the epsilon, the moduli of epsilon stable quasi-maps to X, then this is a proper DM stack over C. We do have a unique limit for every 1 parameter family. And it also has a perfect observation theory. So everything is the same as a stable map case. So it produces a virtual structure, virtual cycle, and a virtual structure sheaf. We can define all those invariants. And the evaluation maps are also well defined because we have required that this or okay, so we have required that this or disjoint from the markings. So at the markings, the map is actually defined. It's an actual map to X. So we do have the evaluation maps. Okay, so let's take a closer look at this stability condition. It clearly has a wall and chamber structure on the space of all epsilons. So the horizontal axis represents epsilon. So when epsilon is great enough, then this 1 over epsilon is some number between 0 and 1. And so this degree and length, they are integers. So it means that this is just greater than 0, and this is always 0. So it means that there's no base point at all, and every rational tail has to have a positive degree. So we see that this reproduces the notion of stable maps, and it does the virtual cycle and virtual stress shift coincide with the Euro ones. Okay. If we cross the wall at epsilon equals 1, then here epsilon is between 1 and 2. So we see that we now allow base points of length up to 1, and we disallow rational tails of degree 0 and 1. So this one is disallowed on this side, but the total degree remains the same. Then we replace it by a base point of length equals to 1. Okay. If you go further, then you remove the degree 2 tails and replace it by a base point of length 2. Okay, it goes on, it goes on. So what's the significance of this is that if you keep going, the total degree is fixed. So at some point, there are no rational tails at all. And the conjecture is that the adjacent chambers at least give it equivalent invariance. So the wall crossing phenomenon just splits off this contribution from this rational tails to the higher genius invariance. And it's most interesting in the case when genius is 0 and n equals to 1. So in this case, the whole curve is just a bunch of rational tails constructed inductively from rational tails. So crossing all these walls just contracts all these rational tails inductively. And eventually, the leftmost chamber is empty, and you can compute everything there. Okay. So the Walker formula is about every genus G, but it actually deals with the genus 0 contribution. So the Walker formula for the Euro invariance cosmological theory, or the Zhou theoretic theory, was conjectured by Fontaine and Kim. It said that the difference between these two virtual cycles has a expression in terms of inductively in terms of other invariants of other virtual cycles. So here, some remarks in order. So here, first of all, this equal is cheating a little bit. So these two spaces, the two cycles live on different spaces, but we can push forward, but they have some maps to some common space. So we can push them forward there to compare them. And or we can just take the push forward to a point and compare them. They all make sense. So I just put quotes here. And the right hand side is a summation over K. And so K is the number of additional markings, K. And at each additional marking, you insert some cohomology classes. And so this corresponds to a splitting of the curve class. And you can think of this as splitting of K rational tails of degrees, each of degree D0, and the remaining degree is beta prime. And at each of those additional marking, you insert some class. This is related to a truncation of the I function, a truncation of so-called I function. I function is defined, roughly speaking, from the a quasi-maps from a fixed P1 to X with a maximal length base point at some point, and it considers a C-star equivalent theory. Okay, so it's just similarly complicated but very effective formula, because the right-hand side we have strictly more markings but strictly smaller degrees. And there's an analog, K-theoretic analog, which is a comparison of the structure, virtual structure sheaves. You can see that it's almost the same, but here we have this SK equivalent invariant theory. Because when you split off the nodes, the tails, the K tails are unordered. So let's look at the geometric meaning of this this Walker formula. It can be schematically pictured like this. So on the left-hand side, I'm drawing this objects in this modular spaces. So here we have base points. Here we have rational tails. And the difference is we split off one rational tail. And this one is appears here with K equals 1. And corresponding to the splitting of the partition of the curve class. And we insert some class to account for this missing rational tail. And we do this for 2 tails and modulo S2 action. And we do this for more, it goes on. Okay. Right, so this is this is so-called the basic Walker formula. It's the one coming directly from geometry, and we can package it into generating functions. We can define the K-theoretic epsilon stable quasi-map invariant generating functions. Here, T is a generic cohomology class, tensor with some lambda ring, and Q is a variable keeping track of the degree. Sorry, capital Q, I'm using capital Q here. Yeah, right, then we can just generating the most universal generating function. Then the Walker formula has a simple form. In GS greater than 1, then the change from this stability is just a shift in the cohomology class. And in GS0, the same is true modulo linear terms in T. Because in GS0, because linear terms are kind of unstable, so we have to they have to take them out. But those terms can be dealt with alternatively using what I said here. So we can contrast everything to a irreducible curve, so and to an empty chamber. So in GN0, we have a different way of packaging. So this is for who's familiar with this invariance. So we have defined the J function. It's usually just one insertion, 1 point. It's called 1 point function. It has one special insertion and the K generic insertions. And if for epsilon stable, we have some unstable terms, and these are replaced by some graph space construction. Anyways, some generating functions that's considered a lot in this enumerated geometry. And then again, they are related by a change of a shift in the cohomology class. Okay, so much for the statement. Are there any questions so far? Oh, I forgot to say, so this is a S infinity because it just means we always take Sn invariant part for various n. Okay. So the idea of the proof is that, so the proof is actually independent of the target. So the idea is to use this so-called master space technique. This is called master space. We construct a bigger space called the master space. The key property that first, again, it has to be a DM stack and proper. And I want to have also have a virtual perfect object theory. And it carries a C-star action. And the fixed loci, one is closely related to this epsilon plus stability. The epsilon plus and epsilon minus are two stabilities on the two sides of the wall. Epsilon 0 equals 1 over d0. d0 is some integer. So crossing the wall just replaces degree d tails minus d base points. So there's a C-star action, and the modular spaces appearing in the wall crossing formula. They all naturally appear in the fixed loci. They're not exactly equal, but closely related to them. Then we can use the so-called master space technique to relate these different invariants. And so the master space technique uses a K-theoretic localization formula. The version we use or recently obtained by Yunho Kim and Michael Savis. So it said that if C acts on a DM stack, and assuming that C star acts on the fixed loci trivially. So this is the tricky part. It's Fi already defined to be the fixed loci, but because this X should be the modular space. The modular space is maybe DM stacks. So the C star might still have non-trivial action on those DMs, on those fixed loci. And basically this orbifoldness is the one that's causing most of the trouble here. But we can always replace this C star action by a N-to-1 cover to make this condition satisfied if given any action to start with. Okay. Then the localization formula says the virtual structure sheaf, we have a equivariant perfect option theory, then virtual structure sheaf is equal to this the virtual structure sheaf for the fixed loci divided by, this is a so-called K-theoretic Euler class. And it holds true if you localize by tensoring with Q, the rational functions in Q. And here little q is the so-called equivariant parameter. It's the universal line bundle of the classifying stack. So what's a virtual normal Euler class? Let's look at the line bundle case. If the virtual normal bundle is a line bundle, then the K-theoretic version, the Euler class looks like this. Okay, and then the Zhou version, the Euro Euler class looks like this, where Z is also the equivariant parameter, the universal class, universal chain class, first chain class on CP infinity. Okay, so the orbifoldness is causing trouble because here this one is always nilpotent, so we can. So this one is invertible once we invert Z, but the left-hand side, it's not clear that the action, this one is invertible. Actually, I haven't seen a proof that this one is invertible after this tensoring with the rational field. Because L might not be in a projective scheme, smooth projective scheme, this line model is always unipotent in the K group. But in the orbifold case, because there is this finite group action, finite isotropic group action coming around, so I haven't seen a proof that this is invertible. But in their proof, they show that this might, we don't know if this is invertible, but the action on K lower 0 of this thing is indeed invertible. So the K theory actually works. The localization works because we want K lower 0. Oh, the master space technique is like this. So consider a sister action on P1. We look at there are 2 fixed points, and if we take just in the classical AGEA-Bolt localization, we look at the cohomology class 1, we integrate that on this P1, then we get 1 over Z and 1 over minus Z. So the Z minus Z corresponding to the weights of the action on the tangent spaces at those 2 points. One is positive one is negative one. So this is 0. So you can see that without knowing the too much about the whole P1, we know that the weights of this tangent spaces at those 2 fixed points are opposite to each other. One is positive one is minus 1. So that's the idea of the master space technique. So in K theory, it works like this. So we have say we have a moduli space X with a C-star action. We have a equivariant map to some invariant map to some space Y with trivial C-star action. So this one can be taken, for example, to be a point. Then the push forward of the virtual structure sheaf, before using the localization formula. So this is inside here. So it's before tensoring with the rational field. You only have poles at 0 and infinity. But the localization formula gives another expression of this one in terms of the fixed loci. So it means that the right-hand side, when pushing forward to Y, also have poles only at 0 and infinity. So the conclusion is that the right-hand side, if we multiply this by dq over q, then the residue at 0 infinity should be 0. It can also, the formula holds true if we multiply this by any K theory class. So this gives a relation among this fixed loci. And in our construction, so this one will have a virtual normal bundle equal to a line bundle. And I want to recover information about these two from this localization formula. So I want the terms to be not too irrelevant, to be closely related to this one. So it is true because for this two ends, these two fixed loci with line bundle as normal bundles, the corresponding term in this formula does actually lose no information. It just recovers the input we give it. So it means that the localization formula, this one is strong enough to get enough information about this two invariants in 2 chambers. Okay, but how do we construct this master space? So the idea is, what if we merge these 2 stability conditions? So on one side, we allow more base points. On the other side, we allow more rational tails. So what if we allow both? If we allow both, then we cross this disallow thing. then we take basically the union of not the union of spaces, but union of stability conditions. But the key observation is that something bad happens because, if we have such a thing, we have both a length d base point and a degree d tail, the automorphism might be infinity. If you have two of them, the automorphism might be, because the quasi-map becomes a constant rational map on this one, on this tail. So if there are two, then it's worse. But that's kind of what we want, because this fixed loci should be the one that has C star as automorphism if we quotient this by C star. So we just need to recover this master space by adding some structure to stabilize this kind of objects. So the idea is, roughly speaking, we attach a tangent vector to the node. It's actually a deformation space, a deformation, minimal and infinitesimal deformation of the node, smoothing of the node. And dual to that, actually dual to that. We call that V, and the C star action, the scale is V. And we impose the condition that if if V is 0, we impose one stability. If it's infinity, we impose the other stability. Then if we follow this trajectory here, then start from V0, then it's fixed. And when V becomes non-zero, then it's scaled by this C star action. And they want to tend to infinity, but we prohibit that because they still have a rational tail yet. So it cannot, but the only way to take the limit is to reparameterize this tail to bring every zero of the fields to this point. So it creates something like this. And then it smooths out this tail, it goes to infinity. V can go to infinity. So you can see that, so this dynamically tells you how this object changes with this C star action. But they have two of them, then and actually the only construction is we add V is a product, the tensor product of these two spaces. And we can reparameterize either of this tail, but we cannot do both, because if we do both, then the automorphism is still too big. But we don't have a preferred choice. So the solution is that we add more information by taking some blow-ups. So we add basically a line in these two deformation spaces. And if the line is generic, then it identifies these two tangent spaces, these two nodes. So the C star action have to scale these two tails in a compatible way. In that sense, we say this is entangled. So this the thing is replaced by a P1, and you can see that corresponding to different initial values of this line, it could be this, or could be generic. We have different trajectories, but the point that the limits is always unique. And so we get that this is a proper DM stack with a perfect range theory, and applying virtual localization formula gives exactly the desired formula. Okay, I'll stop here. Thanks.
Okay. So any question?
Do you have any kind of duality statement between K-theory localization and Zhou localization?
Between the two localizations?
Yes.
I don't know any duality statement. So they are just parallel in a sense, but it turned out that for stacks, the K-theory localization is much harder. The short answer is I don't know any duality statement.
Because naively, to me, K-theorem something is some kind of coherent shift topology, and the Chow group in something is just cycle. So to me, it's some kind of inherent or hidden symmetry between them.
Yeah, they're isomorphic for smooth projective varieties at least. But we all, so in the nicest case, so then the Riemann rock tells you that they're equal, and this virtual localization, I think, becomes also equivalent under that. But the key that I'm dealing with a very not nice case. This is not a scheme, it's the Riemann stack. And it would be nicer, my life would be easier if we know that the course moduli is projected, but we don't even know that. So under some assumptions like resolution property, for any sheaf you have a finite resolution, etc., then it becomes not necessarily finite resolution. So for the most general space, we don't know that there are some technical difficulties. I'm not sure if that answers the question. Sorry.
Thank you. More questions?
Can I ask you a question?
Yeah, go ahead.
So in this talk, you keep talking about virtual fundamental class, right?
Yes.
So what can you say about non-virtual component? Is there any information?
Non-virtual component?
Yeah. Like in the context of derived object geometry, for example.
So I'm not an expert on derived geometry, but the story I heard that that the modular space, if you look at the space itself, it's some kind of truncated version of the derived thing, and the derived thing should be the one we want. And so the virtual fundamental class is not necessarily a component of the modular space. It's just a cycle living in the modular space. So maybe the modular space have several components, or maybe it's smooth. But the virtual cycle is something just a cycle in the space, and it's more relevant to this counting problem. The counting problem give you our observation theory. And if you deform the target manifold a little bit, then the modular space might change dramatically, but the virtual cycle changes flatly.
I see.
Yeah.
Yeah, I just thought the virtual fundamental class it means something with highest dimension.
Oh, no, it's not
okay.
that.
Yeah, thank you.
Sure.
Any more comments or questions? So if no, let's thank Dr. Zhou Yang for the talk. So according to the schedule, shall we return in 15 minutes? Thank you.